Today we begin our study of number systems, which are the foundation of all digital electronics and programmable logic controllers. Everything a PLC does, whether it's reading a sensor, turning on a motor, or storing a program, ultimately comes down to numbers. In our daily lives, we naturally use the decimal system, or base 10, because it's what we've grown up with. But computers and PLCs don't think in base 10. They operate in binary, or base 2, where everything is represented by zeros and ones. That's because at the hardware level, circuits are either on or off, high or low voltage, true or false. Since binary numbers can become long and difficult to read, engineers often use a third system, hexadecimal or base 16. Hex is a compact way to represent binary numbers, making it easier to read memory locations, debug programs, and work with PLC error codes. By the end of this lecture, you should be able to define the decimal, binary, and hexadecimal number systems, convert numbers from one system to another, understand terms like bit, byte, word, and why they matter in memory organization. The base of a number system tells us how many unique digits are used in that system. For example, the decimal system has a base of 10, which means it uses the digits 0 through 9. The value of a number in this system depends not only on the digits themselves, but also on their position, or place value. Each position represents a power of 10, starting from the rightmost digit. For instance, the number 1962 can be broken down into 2 times 10 to the 0 plus 6 times 10, plus 9 times 10 squared, plus 1 times 10 cubed. Adding those values together gives us the total of 1962. This illustrates that the overall value of a number is found by multiplying each digit by its place value and then summing the results. Understanding this concept is important because the same principle applies to other number systems, such as binary and hexadecimal, which computers and PLCs rely on. The binary system is built on the number 2, so it only uses 2 digits, 0 and 1. In digital circuits, it's easy to tell the difference between 2 voltage levels. A 1 usually means the voltage is high, around 5 volts, while a 0 means the voltage is low, 0 volts. This makes the binary system a perfect match for PLCs and computer systems, since they naturally work with just 2 states, on and off. Because the binary system only has 2 digits, each position in a binary number can only take 2 values, 0 or 1. After these 2 values are used, the system carries over to the next position, just as we carry over in decimal after the digit 9. For example, counting in binary goes 0, 1, 10, 11, 100, and so on. Notice how the number of digits increases as the values grow larger. This illustrates how binary numbers expand in the same way as decimal numbers, but with a base of 2 instead of 10. Importantly, all numbering systems start at 0. Here we can compare different number systems side by side: decimal, binary, octal, and hexadecimal. Decimal has a base of 10, binary a base of 2, octal a base of 8, and hexadecimal a base of 16. This chart helps us see how values in decimal correspond to their equivalents in other systems. For example, decimal 10 equals binary 1010, octal 12, and hexadecimal A. These conversions are important because different systems are useful in different contexts: binary for hardware, hexadecimal for compact readability, and decimal for human interaction. The decimal equivalent of a binary number can be determined in a manner similar to a decimal number. This time the weighted values of the positions are 1, 2, 4, 8, 16, 32, 64, and so on. The weighted value, instead of being 10 raised to the power of the position, is 2 raised to the power of the position. This figure illustrates how the binary number 10101101 is converted to its decimal equivalent, 173. Each digit of a binary number is called a bit. A group of 8 bits makes a byte, and 2 bytes together form a 16-bit word. Words are the standard unit of memory storage in most PLCs. Within a word, the least significant bit, LSB, represents the smallest value, and the most significant bit, MSB, represents the largest value. For example, in the binary word shown, The MSB is on the far left, and the LSB is on the far right. Understanding bits, bytes, and words is essential because PLCs store and manipulate data in these fixed groupings. PLC memory is organized into bytes, single words, or double words, depending on the size of data being stored. A word is usually 16 bits, and memory capacity is often expressed in terms of words. For example, if the memory size is 1K word, that means it can hold 1,024 words. Since each word is made up of 16 bits, the total memory capacity in this case will be 16,384 bits. Each of those bits can represent a piece of information, such as the on or off state of a device. The diagram shows how each word is assigned a memory address, with the individual bits inside the word numbered from 0 to 15. This structure makes it possible for the PLC to efficiently organize and access information at the bit, byte, or word level. To convert a decimal number to its binary equivalent, we must perform a series of divisions by 2. This figure illustrates the conversion of the decimal number 47 to binary. We start by dividing the decimal number by 2. If there is a remainder, it is placed in the LSB of the binary number. If there is no remainder, a 0 is placed in the LSB. The result of the division is brought down, and the process is repeated until the result of successive divisions has been reduced to 0. The hexadecimal, or hex system, is a base 16 system. This means that it uses 16 different symbols to represent numbers. The digits 0 through 9 represent values 0 to 9, and then the letters A through F are used to represent the decimal values 10 through 15. For example, the hex digit A corresponds to decimal 10, B corresponds to decimal 11, and so on up to F, which represents decimal 15. Hexadecimal is often used in computer and PLC work because it provides a very compact way of expressing long binary numbers. To convert a hexadecimal number to its decimal equivalent, the hexadecimal digits in the columns are multiplied by the base 16 weight, depending on digit significance. This figure illustrates how the conversion would be done for the hex number 1B7. Hexadecimal numbers can easily be converted to binary numbers. Conversion is accomplished by writing the 4-bit binary equivalent of the hex digit for each position, as illustrated in this figure. In this lecture, we started with the decimal system, the base 10 numbering system that we use every day. We then moved into the binary system, and finally, we looked at the hexadecimal system. Together, these 3 systems form the essential language of digital logic and computer memory. In the next lecture, we will build on this foundation by looking at special coding systems, such as BCD and gray code, which are designed to solve specific practical problems in digital electronics and industrial control.